Okay, this video is going to go through some examples on Lesson 2, Equally Likely Cases for Calculating Probability. And the idea here is that you should be able to look at a problem and then pause the video, try it on your own, and then unpause and see whether you have the solution correct. And in some cases, there might be more than one way to solve a problem. And if that's true, I will try to do it more than one way. But all these will involve the ideas in Lesson 2 that we have equally likely cases. So the probability is the number of outcomes in the event over the number of outcomes in the sample space. Okay, the first one here is a box contains 12 green balls numbered from 1 to 12 and 8 red balls that are numbered from 13 to 20. If one ball is drawn at random from the box, then what's the probability that the number on the ball is odd? Okay, for the solution to this problem, we need to kind of come up with what is the sample space and then also what is the event, right? If we draw a single ball out of a box, then all the balls are equally likely to be drawn. That means this is definitely an equally likely case. So we could say the probability of the ball being odd, right, is going to be a count, which is the number of ways that we can have an odd numbered ball divided by the number of total balls there are to draw from, right? You can think of that as the count in the event divided by the count in the sample space. So let's try to list both of those things. The sample space can be thought of the set of all the balls, right? So first of all, there's 12 green balls that are numbered 1 to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then there are 8 red balls that are numbered 13 through 20. So 13, 14, 15, 16, 17, 18, 19, and 20. This is a set of all the balls, and it doesn't really matter that some of these are red and some of these are blue or green. It just, every ball is a unique ball, and we can identify the ball just by the number on the ball. So really, the number of balls, or the number of items in the sample space here is just the 20 balls. So on the bottom it would be the 20 balls. Then the event, we want to go back and list all of the outcomes, all of the balls which meet the criteria to be in the event, which is that the ball is odd. So if we have an odd, we're just going to list all the numbers that are odd. 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. All the other numbers in the sample space are not odd. And so then, to find the numerator, we're just going to count up the number of odd numbers. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So it'll be 10 out of 20, which is the same as 1/2, which is 50%. So you can write that either as a fraction, 1/2, or even 10 out of 20. You can write it as a percent, as a decimal, 0.5. So correct answers would be 1/2. Or you could also write it as the decimal, 0.5, or you can write it as a percent, 50%. All of those are correct ways to write the answer. Okay, so that's problem number 1. How did you do? Okay, we're going to move on to problem number 2. Same thing, read it and then pause it, try it, and then see if your solution matches mine. For number 2, it says, what's the probability that one number from the following set of numbers will be even? So same idea, we have an equally likely chance of drawing any of these numbers, and they've already listed out the sample space for us, so all we really need to do is come up with the event space. So we're talking about a number being even, so we want to list all the numbers in this outcome sample space that are even. So that'd be the 2, the 6, the 8, the 12, and that's it. So the probability that a number would be even would be the count in the events, 1, 2, 3, 4, right? There are 4 in that event of being even. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different numbers in the sample space. Okay, and then we could also use a calculator to figure out what that is in decimal if we wanted to. So I'm going to go ahead and bring up a calculator on the screen here and show you that we could also convert that to a decimal. So we have 4/9, so if I just take 4 divided by 9 here, 4 divided by 9 is 0.4444, and that means that this is also 0.4444. I will tend to usually write probabilities as decimals, in decimal form rounded to 4 decimal places. All right, so that's the answer to number 2. Let's go ahead and move on. Problem number 3 says to determine the probability of E if the odds are 2 to 9 for E. Okay, so really what this is a not where we're computing the probability, but we're essentially given the probability. We're just given it in the form of an odds, right? So let's remind ourselves what odds are. If we have odds for E, the odds for E are 2 to 9. That means the 2 represents the number of ways that we can win, or the number of successes or yeses, and the 9s are the number of losses, the number of ways we lose, or the number of no's, right? But a probability for E has to be the number of wins over the total number, right? The total number, right? So that would be there are 2 wins out of a total of 9 plus 2 possibilities. So that means it would be 2 over 11. Right? The probability here is the fraction 2 over 11, and we could also do that in a calculator to convert that to decimal. So if I did 2 divided by 11, that is 0.1818. Okay, so that is the probability. It's just odds converted to probability. Remember that probability is the number of successes over the total, and odds is a comparison of successes to failures. Okay, let's move on to the next one. Problem 4 is also an odds problem. It says determine the odds for E if the probability of the event E happening is 60%. So we're going the other direction this time. If we have the probability of E is 0.6, then that is the number of ways that E can happen. This is the number of ways for E divided by the total number of ways. Okay, and if that's 0.6, since we like everything to be in terms of integers for odds, let's go ahead and write that as an integer. 0.6 is the same as 6/10. So that's like another way of saying if I have wins and I have losses and totals here, wins, losses, total, if you want to think of that, then this 6 right here identifies the number of wins, and this 10 is really the total number. So that would let us say, okay, well, if there's 6 wins out of 10 total, that means there has to be 4 losses. So the odds for E happening has to be the number of wins to the number of losses. So the number of wins would be 6, and the number of losses would be 2. And so we would say this, that the odds for E are 6 to 4. 6 to 4. 6 win cases for every 4 loss cases. Okay, that's problem number 4. Let's move on to 5. Okay, it says a group of 10 married couples goes to the movies. 2 of the people in this group are chosen to win a free popcorn. What is the probability that the 2 people chosen are married to each other? Okay, this is a little bit tricky. It's actually a very easy problem if you see the trick, right? So pause the video, think about it. Okay, so there are 2 people being chosen, really, right? Let's draw a picture to represent the situation. Sometimes it's helpful if we have a picture. So I'm going to do is represent each person in this group of couples with a letter. So I'll use A and A to represent 2 people that are one of the married couples. And then we'll have, say, B, and B is another couple, C, C, D, D, E, E, F, F, and so on. There's supposed to be 10 couples, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 couples, 8 couples, 9 couples, 10 couples. Okay, so each of these letters represents a person, and the ones that match are couples. Okay, so it says 2 people are chosen to win a popcorn. What's the probability that the 2 are married to each other? So let's just kind of model the scenario. Let's say that one of the people chosen is this person right here. Okay, that person wins a popcorn. Okay, so the second person has to be chosen, but that person is going to be chosen out of the remaining people, and we're really finding the probability that the second person is H, is the other member of this couple, right? Because that way the 2 people would be married to each other. Well, if you think about it that way, there were 10 couples of 2 each, so there were a total of 20 people originally. 1 person was chosen first, and that means there's 19 people left to choose out of. And then how many of those would be the spouse of the person that was chosen first? Only 1. So in fact, this probability is 1 out of 19. and 1 out of 19 corresponds to, in decimal, 0.0526. So there's just a little over a 5% chance that if 2 people are chosen at random out of 10 couples, that the 2 that are chosen will be married to each other. Okay, next problem, number 6. It says 2 fair 6-sided dice are thrown, and the sum of the 2 dice values is computed. What is the probability that this sum will be a 10? Okay, so if we're throwing 2 dice, we haven't yet studied ways to consider each dice roll independently. We just have ways to talk about equally likely cases. So what would be equally likely to happen? Well, we're talking about the 2 dice and the sum being computed. What we're really interested in is the sums themselves, right? So we're trying to figure out of all possible sums, what would be the probability that the sum is 10. All right, so I think we need a way to kind of to list what we need for the equally likely cases. Let's state it this way. The sample space will be all possible sums of 2 dice. Okay, and the event will be all the sums which equal 10. Okay, so one way to deal with 2 dice is maybe let's make a grid. We've got the first dice. We could have a 1, 2, 3, 4, 5, or 6, and all of those are equally likely to happen. And the second dice could also have a 1, 2, 3, 4, 5, or 6, and that's going to give us different sums. Let's actually, in red here, I'm going to write what the sum is of that. So if I have a roll a 1 and a 1, the sum would be 2. A 1 with a 2 would be 3. A 1 with a 3 would be 4, and so on. Right, these would be the sums. If I had a 2 with a 1, that would be 3. I'm just going to go ahead and fill this. This grid right here is a great approach if you're dealing with 2 dice. You can talk about different sums and quickly kind of list the sample space. Remember, one of the strategies for counting is to list all of the possible values in the sample space. So, and another technique to do that is to come up with a method, some sort of methodology to do that, to make sure that you get all of the cases. So this grid is a good way to methodically list all of the sums. So all those red numbers there are the possible sums. All right, so how many are there? The probability that the sum would be 10. On the bottom of the fraction, we have to list the number of different possible sums. So if I have a grid that's 6 by 6, then that means the area here is 6 times 6, or 36. You could also count the individual red numbers and see that there are 36 different possible sums. And then how many of those are 10? Well, it looks like 3 of those. So it would be 3 out of 36. 3 out of 36. And if I were to use a calculator to get the decimal equivalent to that, 3 out of 36 turns out to be 0.0833. So it looks like 0.0833, just over 8% chance that if I roll 2 dice and add their numbers together, that the sum will be exactly equal to 10. Okay, let's move on to the next problem. Okay, it says if we draw a card randomly from a standard deck of 52 cards, what's the probability that it is a heart? So I'm not sure if everybody knows cards, but let's go ahead and take a quick look at what a card deck consists of. There are 4 what they call suits, and the suits are hearts, diamonds, clubs, and spades. Okay, some of them are black. The clubs and the spades are black, and the diamonds and the hearts are red. And then within each one of those, the following. We have a 2, 3, 4, 5, 6, 7, 8, and a 9. And then we have a 10, a jack, a king, a queen, and then an ace. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards in each suit. And 2 of the suits are red and 2 of the suits are black. So that's what a standard 52 card deck looks like. So it says if we draw a card at random, we're drawing a single card, what's the probability that it's a heart? So the sample space here would be all 52 cards, right? And the event space would be just the ones that are hearts, right? And how many hearts are there? Well, there are 13 of each of those suits. So there are 13 hearts. So if I want the probability that we have a heart when we draw a single card, it would be 13 out of 52. So you could do that in terms of the cards themselves. Another way to get that, and by the way, let's go ahead and do that in a calculator. 13 out of 52. 13 out of 52 turns out to be 0.25, which is the same as 1/4. Right? So 1/4 or 0.25, that would be the probability. If we didn't want to deal with individual cards, we could also talk about suits, right? You could say, well, how many suits are there? The sample space could consist of the suits. We have hearts, diamonds, clubs, and spades, right? And then you could say, well, the event would be that we have hearts, and so that means the probability of having a heart is 1 out of the 4 suits, which is also 0.25. So, you know, whether you think of it as individual cards or the suits themselves, as long as everything in the sample space is equally likely to happen, then both of those are valid ways to solve the problem. Okay, let's move on to the next problem. Okay, this one says a password is made up of 3 letters followed by 2 digits. Janice has a password to her computer account. A, if George randomly guesses a password, what's the probability he will correctly guess Janice's password? Okay. B, if a computer could try out all possible passwords and can check 1,000 passwords per second, how long will it take the computer to try all the possible passwords and definitely find Janice's password? And then C, if the password were made up of 5 letters followed by 4 digits, how long would it take the computer to try all possible passwords? Okay, let's look at the first one first, because that one is the probability calculation. It says the probability that George correctly guesses Janice's password. If he's just guessing and randomly guesses a password, a single password, then for him to guess the password, his guess would have to be the correct password out of all possible passwords. So for part A, I think we need to say the sample space is all possible passwords. Okay, so how many passwords are there? We need a way to count this. Well, we have 3 letters followed by 2 digits. Now, we could do a tree diagram, but there are 26 letters, so the tree diagram would get very large. I think this is a perfect case for us to use multiplication principle, right? Let's talk about the number of ways we could make choices, right? We have to choose a letter. I'll use L for letter. We have to choose another letter, and then 2 digits, which are numbers, digits. So if we have 3 letters followed by 2 digits, then to pick a password, we have 5 choices to make, right? We have to choose a letter. So for example, let's say we chose B, X, X, and then 2, 4. That would be a potential password if a password is made up of 3 letters followed by 2 digits. So how many ways are there to make this choice? Well, we could choose 26 different ways because there's 26 different letters. And it looks like there's nothing in here that there's nothing here that says you can't reuse letters. So all 26 letters would be available for the second letter and for the third letter. And then for digits, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, but there's also a 0. So that's 9 plus 1 more is 10 digits, and then 10 digits. So it looks like if we're looking at how many different ways we could choose passwords, well, there's this many ways to make each of the choices. And we know by the multiplication principle that we would multiply each of those values. So if I take a calculator here and multiply that out, we're going to get 26 times 26 times 26 times 10 times another 10. Okay, so that's going to be 1757600. 1757600. So it looks like there are 1,757,000 passwords possible here. Let me change that here. I want to go by 1757600. 1757600. Technical problem there. Okay, so there are about 1 3/4 million different possible passwords, and that would be the sample space. So for the event space, we have to look at the event we're trying to find the probability of, which is that George randomly guesses the password. So out of all possible passwords, only one of those is the proper password that will match Janice's password. So the probability that that you guess correctly would be 1 out of that 1757600 number, right? Which is going to be very small indeed. Let's go ahead and do that in a calculator. So that's going to be 1 divided by that big number that I still have saved in there. So now this is written 5.69 e negative 7. That e doesn't mean an error. It means exponential notation. 5.6, I'm going to write it 5.69. 5.69 times 10 to the negative 7th, which is the equivalent of having 6 zeros, 1, 2, 3, 4, 5, 6, and then a 5, 6, 9. So an extremely low probability of George guessing the password if he just guesses one time, right? Because there's, 1,750,000 different passwords to choose from. Okay, let's move on to part B. Part B says, if a computer can try all possible passwords and can check 1,000 passwords a second, how long would it take the computer to try all the possible passwords? All right. Well, if now we know from the first part that there are 1,757,600 different passwords, and we know that the computer can try 1,000 passwords per second, so for every 1 second we can try 1,000 of the passwords, then that means that if I take a calculator and take that this number right here, and then I divide it by 1,000, it means it's going to take 1,500 or 1,757.6 seconds for this to get 1,700. What was it? 1,757.6 seconds. Well, okay, that's a lot of seconds. Let's see if we can convert that to minutes or hours. So if I were to divide that and say there are 60 seconds in every 1 minute, and then there is 60 minutes in every 1 hour, if I divide it by 60 twice, that's going to tell me how many hours it's going to take. So let's do that. Let's divide that by 60. That's how many minutes it would take. Actually, that's as far as I want to go, right? It's going to take... let's see, it's going to take 29 minutes. So I'll back up here. I don't need to convert to hours. This would take about 29 minutes. So that's actually not very long for the computer to try all those passwords out. Okay, so part C is asking, okay, what if we increase the size of the password? What does that do to the time it takes for the computer to completely try all the problems and definitely guess the password? So in this part, all we're doing is increasing the number of passwords. This time we have 5 letters, 1, 2, 3, 4, 5 letters, followed by 4 digits, 1, 2, 3, 4, digit, 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 digit. All the letters would be 26 times, and we're going to multiply using the multiplication principle here, and 10 for all the digits. And then the probability, well, actually, no, we're not doing probability, sorry. We're trying to figure out the time it will take. So let's do that same calculation that we did up there, but this time with the larger number of passwords. So first of all, how many passwords are there? Now there's 26 multiplied by itself 5 times. I'm going to save some typing here and go 26 to the 5th power times 4 digits that are 10. So there's that many possible passwords. And if I divide that by 1,000, that's how many passwords per second can get checked by the computer. And then if I can try to convert that, if I divide it by 60, that's going to be the number of minutes. So it's going to take this many minutes. Wow, that is a lot more than 29 minutes. If I divide it by 60 again, that's going to be the number of hours. Wow, so 33,000 hours. Okay, well there's 24 hours in a day, so if I divide by 24, there's 1,375 days, and there's 365 days in a year. So that same computer would take 3.8 years to find the password now. 3.8 years to find that password, where the shorter password could be found in only 29 minutes. This is the reason why there are minimum character requirements for passwords, because as computers get more and more capable, we have to have larger and larger sample space to avoid what we call a brute force attack to find passwords. Okay, let's go ahead and move on to the next problem. Okay, in this problem, it says a bag contains 12 quarters, 10 dimes, and 8 nickels. 3 coins are selected without replacing. A, what's the probability of selecting 3 nickels? And B, what's the probability of selecting 1 of each coin? Okay, so again, if I'm selecting coins out of a bag, every one of the coins is equally likely to be selected, so it's going to be an equally likely case. So we're trying to find the sample space, and we're trying to find the size of the event space. So the sample space here would be the number of ways to select any of the 3 coins. We're selecting 3 coins, so just the number of ways to get 3 coins. Okay, so how can we find that? Well, let's see, we have 12 plus 10 plus 8. So 12 plus 8 is 20 plus 10 is 30. Right, so there are actually 30 coins in the bag. Okay, let's see, out of that 30, we're choosing some. And when we choose one, because it says without replacement, it gets used up. And actually, it's just going to end up in our hands, so order doesn't matter. So I think this actually meets all the criteria for what we would call a combination, right? If you have a set of distinct objects and you choose something, and when you choose something it's used up, then and then the order does not matter. In when we are using the selection, that would qualify as a combination. So we're saying out of 30 items, coins, in this case we don't care about what coin they are, so they're just coins. We're going to choose a combination because order doesn't matter, 3 of those. So there are 30 choose 3 ways to do that. On a calculator we could quickly get that value for the combination. So we have to say 30, and then math, scroll over to the probability submenu, NCR 30. So there are 4,060 ways to pick 3 coins out of 30. 4,060 ways for that to happen. Okay, that's the sample space. The event space here would be specifically getting 3 nickels. The number of ways to get 3 nickels specifically. Okay, so we have to have nickel, nickel, nickel. Okay. So why don't we employ combinations, but well, no, actually I think probably the best way to do this would be to use the same technique we just did, but we have to select the 3 coins specifically only out of the nickels, and there are 8 nickels. So that means out of only the 8 nickels, we have to choose 3 coins. So if I do 8 combination 3, for the same reason as before, it's a combination, so 8 combination 3 this time. Out of the 8 nickels, choose 3, order doesn't matter. That can happen 56 different ways. 56 different ways, and that means the probability of getting 3 nickels is going to be 56 out of 4,060. And I've already worked that out here. That turns out to be 0.0138. 0.0138. So there's about a 1.4% chance that if we draw 3 coins at random out of that bag, that all 3 will be nickels. Okay, so for part B, we're going to take the same approach. We're still drawing 3 coins, and so the sample space will be the same as before. There are 4,060 ways to draw 3 coins, but this time the event is different. We're talking about the number of ways to get 1 of each coin, right? 1 of each coin. So the number of ways to get 1 of each coin, well, let's see. We have to have a nickel, a quarter, we have to have a nickel, and we have to have a dime. So we're going to select 1 of each. So we're doing the same thing as before. We're doing a combination, and we're selecting 1. But each of these has to be selected only from their corresponding numbers. Just like up here, we did the 3 coins had to be selected from the 8 nickels. Here we're selecting 1 quarter. and there are 12 quarters. Here we're selecting 1 nickel, that's out of 8, and then 1 dime out of the 10. And because of the multiplication principle, we should be able to multiply those numbers. So it turns out that if you do combination, 12 combination, combination 1, that's just 12, which kind of makes sense. If you want to know how many ways to select a quarter, and there are 12 quarters, well, it makes sense that there are actually 12 different quarters to select. And there are 8 different nickels, and there are 8 different and 10 different dimes. So if I multiply, let's see, 12 times 10 times 8, that turns out to be 960. And so the probability that we would get one of each would actually be 960 out of the 4,060. And that turns out to be 0.2365. So it's actually more likely that we would get one of each coin than that they would all be nickels. Okay, that's problem 9. Okay, so we can go ahead and go on to problem 10 now. In problem 10, it says a bag contains the following letters, and there's a big list of random looking letters here, but some are duplicated, I notice. It says if all the letters are drawn out of the bag one at a time, so we're going to draw every single one of the letters, and we place them in a line in the order that they're drawn, so the order matters here, then what is the probability that the word mathematics will be formed? All right, so it looks like what we're saying is, how many ways can I line up these symbols so that this specific ordering happens? And there are duplicates here. So this is actually the special case that we call a distinguishable permutation. All right, so, but every one of the possible orders of the letters is equally likely. So, so the sample space would be all of the words that could be formed, right, that are distinguishable, all of the distinguishable words. So maybe I should insert that, all the distinguishable words that could be formed. It's a distinguishable permutation. So there's a formula for that, and it's that the number of permutation, the number of ways to line up things where there's duplicates is n factorial over n1 factorial times n2 factorial times n3 factorial for all the symbols. So here, let's see, I guess we have to count this up. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters to line up. There are 2 A's, so there'd be 2 factorial here. There's 1 C. There's 1 E, there is 1 H, there's 1 I, there's 2 M's, and there's 1 S, and there are 2 T's. So technically that's the complete formula, but really the 1 factorials are all just 1. So the way I would really do the problem is I would say there's 11 symbols, so I'll put 11 factorial on the top, and I'll only look for things where there's at least 2. So there's 2 A's, there's 2 M's, and there's 2 T's. All the other ones are 1. So I have a 2 factorial times a 2 factorial times another 2 factorial. 1 for the A's, 1 for the M's, 1 for the T's. Factorial is also in the in that same menu on the calculator, or we could write this out. This is small enough we might be able to write it out. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1 times 2 times 1. And the ones on the bottom really don't matter. So really, I just need to take 11 factorial and divide it by 3, or divide it by 2 3 times. That's the fastest way to do it in the calculator, so I'm going to do it that way. 11, and then math, probability menu. The fourth item down is factorial. That's 11 factorial. And then I have to divide by 2, and then divide by 2 again, and divide by 2 again. So it looks like the sample space contains, let's see, 4,989,600. Right? So there are 4,989,600. 4.9 million, almost 5 million possible distinguishable words that could be found by lining up the letters in this grouping of letters. All right, so that's the sample space, the count of the sample space. The event is going to be specifically the alignment that is mathematics. That's only one of the alignments, and that means the probability of getting the word mathematics is 1 out of all of those distinguishable permutations. So it would just be 1 over that large number. So if I just take 1 divided by that number, that turns out to be 2 times 10 to the negative 7th, approximately. So 2 times 10 to the negative 7th, which is the same as 1, 2, 3, 4, 5, 6 zeros, and then a 7. So very, very low probability that if we just lined up all of those letters randomly by pulling them one at a time out of a bag, that it would form the word mathematics. Okay, move on to the next problem here. It says, people are entering and leaving a large office building throughout the day. At this instant, exactly 1,000 people are currently inside a building, 582 men and 418 women. A person is about to leave the building. What's the probability that this person is a woman? Okay, so a big word problem here, but actually this is pretty straightforward. It's every person, every person that's in the building could be the person that's about to leave next. So this is an equally likely cases. The sample space would be all the people in the building, and that's going to be the 1,000 people. The event would be, since we're finding the probability the person is a woman, it'll be all the women. And so the women is 418 women, so the probability that the person leaving is a woman is just going to be 418 divided by 1,000, which is 0.418. So, just because something's a word problem doesn't mean it's necessarily difficult. It's still identify the total number and identify the number in the event. Okay, I think just probably 4 problems left here. I know we have a lot in here because there's so many different counting strategies. But let's move on to problem number 12. It says, if you are dealt 5 cards from a standard 52 card deck, what's the probability of getting a pair? Now this one's actually quite tricky, even small number of words here, but actually quite tricky. So we're talking about the probability of getting a pair. So let's just kind of model what that means. A pair means that 2 of the cards in your hand have to be identical, and then the other 3 cards all have to be different from the first one and different from each other. So I'm going to use letters here. AA could represent anything, right? It could be like 2 jacks or 2 twos or 2 fives. And then B would just mean something other than whatever the A's are, right? Okay, so that's what a pair looks like. So, so the sample space would be all 5 card hands. It says you're dealt 5 cards from a deck, presumably at random. And so if there's 52 cards in a deck, we're selecting 5 cards out of that. We're using up a card each time. And the order doesn't matter because they just end up in our hand. That meets the criteria to be a combination. So there'd be 52 combination 5, which I think we've seen this enough in the calculator just to go right to this. It's 2598. 600. So there are about 2.6 million 5-card hands that you could be dealt. So that's the sample space. Okay, for the event space, we have to specifically have all the pairs. Actually, not just all the pairs. It's all hands of the form A, B, C, D. Something where we have 2 cards the same and the other 3 cards are different. And that can be in any order. All right, so since we're counting here, let's talk about the different choices we have to make. Well, the first thing is we have to choose what card is the pair going to be, right? What card are we going to have a pair of? So we're going to choose the A card type. Like, is it a jack? Are they going to be 2s? Are they going to be 5s? So there are 13 different choices, right? There's ace through 10, which is 10, plus jack, queen, king, which is a total of 13. And we're choosing one of those. So I could write just 13, or just for more generically kind of consistent, I'm going to say out of the 13 different cards, I'm choosing one to be the type of card that we're going to have the pair of. Okay, and then I have to talk about how many ways are there to get 2 of the A cards, right? Well, in a deck, there are 4 of each type of a card, right? There's a heart, a club, a diamond, and a spade. So let's say, for example, that we chose jacks to have the pair of. Well, then there's 4 jacks in the deck. So out of those 4, we have to choose 2 of those to be the pair, okay? And then we have to make another choice. We have to choose the B card type. In other words, what are we going to have for the card that isn't a jack, the first card that isn't a jack? Let's say, for example, it's a 4. Okay. Well, how many ways are there to choose that? We can't choose the jack because that was already chosen for the pair. That leaves 12 different card types left, and we have to choose one of those. So 1 out of the 12, for example, a 4, right? And then we have to say, actually, I think that's actually incorrect. I'm going to back up for a second. I don't want to choose that separately. And yeah, let me back up for a second. I would say we need to choose 3. Okay, so we picked the pair, but now we need to pick the rest of the hand. And the reason I'm going to say that is because there are cases where the B's are duplicated, and the C's are duplicated, and the D's are duplicated. But if we choose it all at once, we can choose it so that we can make sure that not only are they different from the A's, but we can make sure that they're all different from each other. That actually becomes very difficult to do if we try to do it one card at a time. So let's say it this way. We have to find the number of ways to pick the B, C, and D cards, to pick which card, the types that we're going to, the card types. In other words, are we going to have 4s, 8s, and a 4, and 8, and a 3, or are we going to have a queen, an ace, and a 2? What are the number of ways to pick the rest of the hands so that they don't match each other, but they also don't match the card that we have the pair of? All right. So how can we do that? Well, I think we would say we have to choose. There are 12 types of cards left. Like, for example, we can't choose the jack, so we could choose anything other than jack, right? But out of those 12 types, we have to choose 3 different ones. So we could choose, for example, let's say we could choose queen, ace, and 4. So we're choosing 3 of the 12 remaining card types to be the types there. And then we actually have to choose those cards, right? We have to choose the B card. In other words, out of the 4 queens, how do I choose which one to include? So there would be 4 queens, and we'd choose one of those. We have to choose the C card. So out of the 4 aces, for example, we have to choose one of those. And we have to choose the D card itself. So out of the 4 4s, we have to choose one of them. And then we would multiply all of those numbers. So rather than show that in the calculator, I'm going to go ahead and show what that turns out to be. If you do 13 combination 1 times 4 combination 2 times 12 combination 3 times 4 combination 1 times 4 combination 1 times 4 combination 1, that turns out to equal, let's see, well, I guess, yeah, I could fill these in. This is, yeah, the whole thing turns out to be 1098240. Okay, and so that means the probability that we would get a pair is that number, 1098240, out of 2598600. Which turns out to be about 0.422. So actually, pairs are one of the lowest hands in games like poker because there's a 42% chance you're going to get one at random just when you're given 4 cards. Okay, so just compare something to the last problem, right? lots of words in problem 11, and that turned out to be a very straightforward problem. Just a single sentence in problem 12, and that's actually probably the hardest problem we've seen in the problem set so far. So you can't correlate how hard a problem is going to be from looking at the amount of words, right? This one was really tricky because there are so many different decisions to be made if you are selecting to get a pair. Okay, let's move on to the next problem. Also a little tricky. It says in a group of 3 people, what's the probability that at least 2 were born in the same month? All right, so there are 2 ways to solve this problem. There's an easy way and there's a hard way. I'm going to go ahead and do the easy way first, and then we'll talk about the hard way and why we really don't want to do it that way, but we'll go ahead and do it just to show that it would work as well. Okay, so the first thing is, whenever you see the word at least, you should at least consider whether it's easier to find the probability of this or to find the probability of the complement of what we're finding, right? So we're trying to find the probability that 2 people of 3 have the same birthday, birth month. Okay, so the complement of that probability is equal to 1 minus whatever the opposite of that is. So what's the opposite that 2 of the 3 people, at least 2 of the 3 people, have the same birth month? The opposite of at least 2 sharing the same birth month is that none of the 3 people have the same birth month, that none match at all. And it turns out that that's easier to find the probability of than the probability that at least 2 were born in the same month. So let's try this. This is actually the easy way to solve the problem. Okay, so what's the probability that none match? Well, we would have to first say that the sample space is all. This is going to be the number of ways to have 3 months, if I don't care whether they match or not. So let's say that there's 3 people, so there are 12 months for the first person to be born in. There's 12 months for the second person, and there's 12 months for the third person. So 12 times 12 times 12 turns out to be 1,728 different groupings of 3 months that we could have there. All right, but E, that's going to be the number of ways where we can have 3 months that don't match. Okay, so same thing, we have to have 3. All 12 months, the first person could be born in any month, but if we want something not to match, the second person would have to be born in one of the 11 remaining months, and then 10 for the third person, so that none of the 3 match. That turns out to be 1,320. And so the probability that none match is 1,320 over 1,728. Right, which turns out to be 0.7639 about. And so the probability that at least 2 do match is 1 minus that, which would be 0.2361. All right, so that is definitely the best way to do it. And I realize that's not super easy, but that's much easier than the alternative. So 0.2361, and it's easiest to find the probability of the opposite. Okay, let's try to do it the other way though. Let's try to do it by finding the probability that directly of all the ways that people can have at least 3 born in the same month. So I'm just going to erase this and do this over again, the second way. Okay, so the sample space will be the same, right? It's just the number of ways to have 3 people choose birth months, right? So that part would be the same. Sample space would just be 12 times 12 times 12, right, which is 1,728. But what if for the event space we look at the number of ways that at least 2 share the same month? Okay, I'm going to represent that in different ways. So I'm going to say, let's say that that A represents one of the months, okay? We could have this situation. The first person and second person share the same month, but the third person doesn't, right? But it could also be ABA, right? Or it could be BAA, or it could be AAA, right? In other words, these first three are all the different ways that two people could share the same month, but you got to account for the fact that it could be the third person that's the one that's different, or the second person, or the first one. And then also, if all three shared the same month, that would still meet the criteria of at least two being born in the same month. So all of those ways are possible ways to do that, right? And if we did our idea of using a multiplication principle for each of these, we could figure out the number of ways for that to be true. So if the first thing, we would have to choose a month for the first person, that would be 12. But if that were true, if the second person had to be born in the same month, there's only one way that that could be done. It would have to match whatever the choice is for the first person. And then for this B right here, we would have to choose out of the 11 remaining months. So there are 12 times 1 times 11. There are 132 ways that the first two people could share a birth month, with the third person being a different month. And if we did the same thing here, right, there would be 12 ways for the first person to have a month. The second person would have to be one of the 11 different ones, and the third person would have to match the first one, which means there's one way to do that, which is also 132. Here we would have 12 months for person B. This has to be different, so 11 months left, and this one would have to match the second person's month. Only one way to do that would be 132. And here, there would be 12 ways to pick the month for the first person, but the second person would have to be the same month, only one way that can happen, and the third person would have to be the same month, only one way that can happen, so that would be 12. So if you add those all up, that turns out to be a total of 408 different ways for there to be two people that have 1 month's birthday and the third person with a different one. And so the probability that we would have at least two do match would be 408 out of the 1728, which turns out to be that same 0.2361. Right? So this is the, if you want to think of it as the additive way, and the other way is the subtractive way. The first way was easier though, because we just didn't have to account for 4 different orderings of that, right? There's only one way for none of them to match. So I guess one thing I would notice is if you see the word at least, you should at least consider doing the complement. Often that's easier in those cases. Okay, let's see. What do we have? 1, 2, just 2 more problems to do. Okay, so this says a produce vendor receives a crate containing 10 apples. 40 apples. 8 of the apples contain worms, although it's not possible to see which ones contain worms visually. If the vendor randomly selects 12 apples to fulfill an order, what's the probability that exactly 3 of the apples in the order will contain a worm? All right. So in this case, let's see. Let's draw a picture. We've got 40 apples. 8 of the apples contain worms. And that means there's 32 apples with no worm in them, right? And then what we're doing is we're going to randomly select 12 apples. So we're selecting 12, so a sample of 12. And we want to know the probability that exactly 3 have a worm. So 3 would have to have a worm. And that means that 9 of them would have to have no worm. Okay. So the reason I'm drawing it this way is because this is really a counting problem, right? The sample space is going to be all ways to select 12 from the 40 if I don't care about worms or not, and by now we know that's 40 combination 12. But when we get to the sample space, it's going to be specifically the ways to get exactly 3 worms and 9 non-worms, right? So that means that we have to select the 3 worms out of the 8 that don't have worms, and we have to select the 9 apples with no worms, specifically out of the 32 that don't have worms. So for that one, we could say, well, we have to select the worm apples, and we have to select the no worm apples. And so we have 8 worm apples to select out of. We're selecting 3 of those. And we have 32 no worm apples, and we're selecting 9 of those. And we would use the multiplication principle, right? So the probability that we'll get exactly 3 worms, right, in a sample of 12 there would be 8 combination 3 times 32 combination 9 divided by 40 combination 12. And when you plug all that in your calculator, since we've done that before, I won't use up more time. This video is getting quite long. That turns out to be 0.2811. All right, good. So one last problem here, and then we'll wrap it up. So the last one, it says 6 letters with repetition allowed are selected from the alphabet. What's the probability that none of the letters are repeated? All right, so again, we're going to use the idea that we list the sample space and we list the event space. So the sample space would be 6 letters selected from the alphabet. So the number of ways to select 6 letters from the alphabet, I think we should use boxes and multiplication principle here. So we have to select 1, 2, 3, 4, 5, 6 letters. Letter, 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 letter. Let's see, there's 26 letters each time, right? So if there's no, I'm just looking at all the possible ways to select the letters, the 6 letters. There's 26 times 26 times 26 ways to do that, right? And then the event space would be, we have to do that same selection, 1, 2, 3, 4, 5, 6 letters, except this time none of the letters can be repeated because we're finding the probability that none are repeated. And so that would be all 26 letters could be done at first, but then we can't select the first one, so there's only 25 letters left, 24, 23, 22, 21. So we could try plugging that all in a calculator and doing that. You could also note that this is the same as 26 to the 6th power, and this is actually the same as having 26 letters and selecting 6 where order matters. That's actually the same as a permutation. So a compact way to write this, probability of having no letters matching, would be, there'd be 26 permutation 6 over 26 to the 6th. If you plug this in, you could also just write it this way. It's 26 times 25 times 24 times 23 times 22 times 21 over 26 times 26 times 26 times 26 times 26 times 26. And that turns out to be 0.5366. Okay, so this video became quite long, because almost an hour, because there are so many ways to count, right? I mean, the underlying structure for these kind of problems is very straightforward. It's just the sample space, count that on the denominator of the fraction, and then find a way to count the event space and put that in the numerator. In the later videos, we're going to talk about more complicated structures, but the counting will generally be much simpler. In fact, this first lesson, lesson 2, covers what I think are some of the most complicated probability problems at all.